and then the salt is concentrated under, and the fresh water is freshening the upper part. So we have a few things: stable stratification. We will see that in a minute, and we have dissolution of salt that forms a brine that is now just dissolved the salt, and it is overlying the salt crystal. It is lying at the lowest part because it's the densest part of the water column. So we have a very, very stable water column here. So this is one region, the wetter region. The dry region is this one, same amount of salt, but now have a good view on that. Okay. Are you able to identify the processes here? A very quick vertical convection led by the interaction between fresh water that is in the upper part and the salt crystal. At that point, we have thermodynamic process of dissolution, and the brine changes its properties dramatically. It becomes saltier, denser, and then it sinks. And the other waters, which is fresh water, is rising upward. So we have vertical convection, very unstable water column. It's very important, we will see it later on in the lecture, to get this, but what we will see in a few minutes, that the salt crystals here will be finished. Unless we add too much salt, and the entire water column will get to saturation and the process will stop. But until then, this is an ongoing unstable stratification. And here we have another water body that it is very stable. The maximum that you can see is just air bubbles that are escaping from the salt crystal, but the solution is very, very limited, because once it stops, it stops. It starts, it forms a brine that is, saturated and very dense. And once it is saturated, thermodynamically, the process is gone. And hydrodynamically, also, the process is gone. The only thing that occurs here is a molecular diffusion that migrates the ions upward, but it is a very slow process compared to this one. I can add some of that, one drop of food color to each. Okay, so it reaches the barrier there down, and you see, but it is not mixing so much. Okay, I will put another one. It sinks very fast, and it will reach a barrier, a density barrier. Here, if I put it, you will see that it is. I'll put two of them. That it will just mix down, and it will not preserve its properties. And this is an expression of the turbulence here, the vertical mixing. So you see, everything is. You can follow the green, wakes going down. Okay, so an introduction to physical oceanography, a bit of chemical oceanography, and this will go on, and we will see finally that they will end up with very different results. Okay, but we want to start from evaporation to evaporites. So evaporation is clear. It's a process that consumes energy and water molecules from the water body and take it up to the atmosphere, makes the lake more salty, and then evaporites is the final product, is the salt layers. That's how in geology, that's the name we give this member of rocks that are formed by a mineralization or formation of minerals by evaporation. So we have gypsum, aragonite, and other members. Salt is the most important in terms of volumes on Earth. So this is what we are heading to understand the series. So, and this small experiment is in between. It's maybe hidden here too, because there are transport processes that we have to follow to understand the links. Or I can say it in another way. You are aware of salt productions in Israel, in Atlit, but worldwide, it's a technology that exists over millennia. And so it's even in the, 2,000-3,000 years ago, mankind already understood that if you isolate a part of the ocean, it's very clear. but it's always very shallow, and it's very clear the process. You take a part of an ocean, you disconnect it, you do it in the summer, you allow evaporation to make the brine saltier until you reach saturation, and from there on you have production of salt layers. So it's very simple from evaporation to evaporites. Should be very simple. I will show you here that when we go to larger water bodies, the transport processes are making this very simple translation much more evolved, and the outcomes are very different. Okay, the team. Good. Okay, so we have here Igor breaking the salt rocks from from a cable. That's the main job, and then other students that are working, PhD students that are working on these projects. Globally, salt layers are very important. You see a global, you don't see it so much, so beautiful, but yeah, this is a global map. Salt layers are in dark colors. They sometimes reach a thickness of thousands of meters and more. They are very, very thick. So if you want to imagine what kind of ocean can produce such piles of material in these places, it's kind of challenging. And even here in the Mediterranean, off Israel shores until Gibraltar, they are huge. It's called salt giants. They are underlined below the floor of the Mediterranean Sea, thousands of meters of halite deposits that were formed in the Miocene, in the Messinian time. It's about 5 million years ago. And the process is very interesting. We are not sure, but closing the Gibraltar Straits, okay, that's one option, but how do you form? And so there are many questions there. I will take you to these questions. So it's a big issue. And another thing that you can see, if you can see the coastlines of Africa and South America, from the tectonics, that they were once together, we think, and they spread. We have a lot of evidence showing that. And during this early part of the spreading, you see salt giants here and here. It's the early breakup of the continents where ocean managed to fill in some deep basins and then limited the connection to the ocean, and then formation of that. As geologists, you finally have the rocks. But what is the story behind that? It's not so clear. So we try to make the puzzle together. We have too few pieces for a huge puzzle, but that's our job. Yeah, so this is one example. It is well agreed that by geologists that these salt giants are formed in perennial hypersaline water bodies and not in a seasonal wet and dry basin. And you need to form a large salt layer, you need continuous crisis, hydrological crisis, negative water balance. Otherwise, salt is not formed. Without negative salt balance, it's very hard to form salt layers. So it's the evaporation that takes the water out and leaves you with the iron, forming the crystal. Deep and wide, this is because of consideration of the huge extent of these. So we need to find that deep is only the Dead Sea is the only deep basin that exists today on Earth. So that's why we will go to the Dead Sea. And this is the map of the Mediterranean. These are the salt giants between the Gibraltar Straits and the Israel. You see the colored region are mostly occupied by salt layers. Again, very thick. This is how it looks in a cross section. So this is the salt layer coming upward, and there are many questions here. And the community working on this problem, mainly in Europe, they, in a review paper, they were writing this sentence as the next steps that the scientific community can do. So they say, in the near future, Messinian is the timing of this event. Research will require more involved involvement of scientists working on modern Earth processes and environment. So modern, we need to find the processes inside to observe them because it's too hard to reconstruct from geology parts of the puzzle. The solution to several of the current open methane and salinity crisis questions requires a much deeper knowledge of modern extreme environments and conditions which undergo large amplitude, aerial or seasonal physiochemical fluctuations. So this is our job. We enter to this niche and try to resolve these problems by direct observation. So let's go to our playground, the Dead Sea. So it's you know, it's the lowest place on Earth. I should update that. No, it's quite okay. Okay, no, that's okay. A tectonic depression. So we are sitting in a plate boundary, and along this plate boundary, we have several water bodies that lay along this depression, tectonic depression. The saltiest one is the Dead Sea, and we are exploring that in this case. It's a terminal lake, meaning that the water is collected from this watershed, mostly from the north. Climate, the Mediterranean and arid. And the reason that the Dead Sea level is declining, as you all know, is because we, Israel, Syria, and Jordania, took all the water by dams. So the water is hidden behind dams, and from the dams it goes into our usage for drinking and for irrigation and so on. And also the Dead Sea industries in Israel and Jordania are keeping these regions still wet, and then we have more evaporation, so it's another consumer. So this is the lake level curve. I don't know if you see good enough, but this is minus 400 to minus almost 430 from 1976 to 2014. I should update that. And this is the dock that was active in 1994. This is a picture from 1994 when this the level was here. And since then, the level is dropping in a rate of about 1 meter per year. When I started working with the GSI, we were stepping to the boat here, and today it's over there and even lower than that. So this is the level curve, man-made. So because of water diversion. Since 1980, halite precipitated from the lake, and this was the first description. It's called Yam HaMelach, the salt sea. But salt was observed in modern times only in 1980s by scientists from Weizmann Institute and Geological Survey and so on. And since then, we have precipitation of salt. Okay, and the rate of precipitation is about, calculated, is about 1/10 of the water level drop. It's about 1/10 of that, 10% of that is you will find accumulation of salt. So here already, we would expect to see massive salt layers, and we don't find them. And this is an interesting question. So in places we find, in other places we don't find, but in this picture we don't find. And I have here a few questions that will be the outline of this talk. How fast these rocks are formed. So these are the fastest sedimentary rock in the record that we know in geology. So sedimentation, the fastest is by salt deposition. So what limits the rate of halite deposition? This will be the first question. To work on that, we will talk about air-water interaction. Then when the deposition is occurring. So as I told you, if you go to Atlit, to the ponds there, they work only in the summer. This is the same in the deep water body. So we will explore that. The seasonality, but also depending on the depth. And then where is the halite deposited? In the air water surface where evaporation takes place, or in other places, and how it is related to the scalar fields of temperature and salinity, which are by themselves, as you know already, are related to the hydrodynamics and are influencing and influenced by thermodynamics. So we have hydrodynamics, thermodynamics. It's quite a complicated story here. So it's more involved in terms of dimensions. And then we will ask after where. Yeah, so also we will ask in the same where, what is the influence of freshwater inflows, which always occurs. And then finally, how can we interpret the geological archive? And we will get into that. So I started with physical modeling, but I thought it wasn't so productive. So I switched to direct observations. So this is my lab's logo, the Dead Sea Observatory, and we have devices of eddy covariance and oceanography, measuring systems, and many instruments that we implement in the Dead Sea to measure air-water interactions and the scalar fields in the water column, and finally to analyze the sedimentology. So you see, this is a pen. So here is a rock record, and we have our friend Reuven. It's the robot, underwater robot that is helping us to explore the lake floor. Some background about the Dead Sea. So the level is dropping because of main usage of water. So salinity is basically rising, but this is in the upper layer. Okay, so the lake is now divided into two. I hope that this will be the last term I will use. Here, epilimnion and hypolimnion relates to the upper and water parts of the lake. So the epilimnion became saltier until 1980, when these scientists observed first appearance of salt crystals, and also the lake switched from stable to unstable water column. And this is related to where you are placing the salt and water, right? So until here, water is placed over the saltier part, so it's stable and not forming any salt. From here on, we have overturns because of higher salinity located in the upper part and because of evaporation, and then we have overturns. So this is the saturation of halite. Since then, we have two things, overturns and the formation of salt. And it's not by accident. That's part of the game. You cannot have salt, well, it's very hard to arrange a basin to precipitate salt if it's not overturning and have very good connection vertically. And when you have dilution, you're getting back to meromictic conditions over volumictic conditions. So this in terms of water column stability, it's a measure in terms of energy. For example, how much energy I should put in to mix this water column. So here it's very stable. And here it's very unstable. So to mix that, I will have to add a lot of energy. So this is the stable part, meromictic, and then volumictic. Yeah. So let's start with the first question. How fast can we get halite deposition? As I told you, from mass balance, it's about 1/10 of the missing water that will form a salt layer. So if we have 1 meter level drop, we will form 10 centimeter roughly. And what is of a salt layer? So the next question will be, what is controlling evaporation rate? So how fast we can go with the formation of these rocks will depend on how fast we can evaporate. To answer this question, we have to think of the heat balance equation or the concept of heat balance, that we think that the incoming radiation is the forcing, and on the other side we will have a series of processes that takes the energy to other resources, such as evaporation, sensible heat flux. These are both turbulent fluxes and stored heat flux. So if you shut these and we don't have no evaporation, no sensible, so we will have stored heat flux. So the water will be warmer as we add more radiative heat. But in nature, these are strongly opened, and these regulate the temperature of the water, and there are very strong feedbacks here. And this is how we can get some answer to that. So if you ask how much evaporation we can get, the maximum is by the energy that you get from radiation, from the external. If there are no other sources of energy, so that's what you can get. And this is roughly 1 meter or a bit more, but well, in other places, in Lake Kinneret, it's more, in other places, it can be even more, but when you go to saltier water, then evaporation goes down because of salinity, and then it's very hard to cross the 1.1 meter per year of evaporation in the given radiation force. So this is how, this is the upper limit. And this is what we found also in the geological record when they managed to have dates in salt records. The maximum they get is approaching this limit. And this is process-wise, this is the, I think, the explanation. You cannot not get more than you insert. Yeah, so the limit of halide deposition is by the heat balance or the incoming radiation that is going out as evaporation flux, and other consumers, but this is the maximum that we can get. But other thing is the wind. So the wind, as you know, is departing the coastline at noontime in summer, and it is and the front is migrating this direction and reaching the Dead Sea during evening after sunset. So we have a very interesting problem here where a long time, this is the diurnal cycle. So so this is sunrise, sunset, this is radiation. So the maximum radiation is noontime, of course, and this is nighttime. And this is when we expect to see highest radiation. And here we have also water temperature, so there is some lag, so it may be in some lag afterwards, about 3 hours. But when we observe the evaporation, we see that we have a double peak here. So in sunrise and sunset, it's almost nothing. And the maximum evaporation, these are the rates here, millimeter per hour. So the maximum evaporation we get is during nighttime. Why is that? Because if we follow the wind speed, we see that it is taking off. It is coming into the Dead Sea only after sunset, and this is how we get kind of charging of energy during the day, but and then part of the energy is escaping as evaporation flux, and the other part is still stored, and this is related to the big water column. So the energy is stored in a big water column, so it has a large storage, and it is released when the wind is taking up during nighttime. So this is just one example of how it looks like in more details, and the way we get, so we can go in even to the heat fluxes. So the 4 main heat fluxes are the net radiation, diurnal cycle. This is the stored energy. It's a bit tricky how to measure it. We have to measure it by that better than me. And this is how the evaporation, as I showed you earlier, looks like. This is the sensible heat flux. It's much lower. And overall, the energy budget is closed over 1 day, so we are fine here. And in the Dead Sea, over a year, the evaporation rate, as I told you, is 1.15 meter per year. And this is limited by the high salinity. In Lake Kinneret, as Shmuel was showing, it's much higher than that, almost 1.5 meter. Okay, so after evaporation, let's ask the next question. When are we depositing salt? So I would say when the water balance is most negative, and this is during summer. So this is the lake level over time, 2.5 years. And during summer, you see that the slope is highest. And if we take the time derivative, so this is a change in, in lake level. This is 0, and these are negative values. So in the dry season, we have fastest level drop, and I would expect highest formation of salt crystals here. And during the winter, slower. That's the first expectation. And if we follow salinity, it shows the same picture. Highest salinity during summer, not surprising. But when we take into account also the temperature, which also influences the saturation of salt, then we have a bit of a challenge here, because saltier and warmer. So the warmer we are, the more ions we can dissolve. So which is the winner, the saltier or warmer? And to answer that, we have to understand the relation between saturation and temperature and salinity, and temperature and salinity by themselves change with time, with the seasons. So when do we expect to see that? And the answer first is by our observations. We managed to develop a very precise way to measure saturation in our lab. So we see that indeed during the winter, we have super saturation and highest formation of salt. And during summer, we have under saturation and dissolution of salt in the Dead Sea during the summer, and during the winter, formation of salt. Why is that? It's very surprising. It's not what we know from our daily experience in Atlit and in Elat and in other places where we see salt factories. They produce during summer, not during winter. So why is that? And also in the literature, it is not occurring. So what is going on in the Dead Sea? I'll tell you another story. There are two captains there, with the boat skippers, one in the northern basin and one in the southern basin. In the northern basin, his name is Shachar. Shachar in the summer is happy because it's hot, but the engines are all open, dissolution, under saturation, no problems with the motor. At the same time, I don't know his name, in the factories there, it's blocked. They have to open it all the time because the salt crystallizes over the engine. So what's the difference? We are in the same hydroclimate. What's the big difference? So the answer is, and in the winter it's the other way. It's very nice there, nice weather, but Shachar has big problem. He has to open the motor in the winter, and the opposite in the Dead Sea factory. So why it's happening so differently? The reason is the thickness of the water column. In deep water, in the deep lake, compared to the shallow lake, we start in the winter at the same position, but as we warm up the water, in the deep lake, we go along this trajectory. The water column because it's very thick, so it's getting only a little bit saltier, and in the shallow water body, indeed it's getting much warmer, but also much saltier, and compared to the saturation curve, this is the big difference. So this is going along this trajectory, the deep lake, and the shallow lake is going to the super saturation. So they spread over two very different situations, and I'll try to explain that very shortly. If you miss that, no problem, we can continue later on. So we have two basins, we evaporate the same amount, let's say, and here we started at the same salinity. When we take such amount of water, the salinity here will rise a lot, and here only little because of mass balance. So we can write a mass balance, and the ratio between the thicknesses is the ratio between the salinities. So the shallow water body will become much saltier. That's fine, but still they will form the same salt layer because we multiply finally the extra salinity by the volume of the water column. We will get the same result. So until now, we can use these to get conclusions about the shallow regarding the deep. So until now, we are okay. But now, let's... When we take into account not only the salt balance, but also the energy balance, as we talked earlier, so the stored heat flux, let's say that we shot evaporation and everything. So the radiation in equals the stored heat flux. And now they should be, we should get the same result. The shallower water, you know, as we have in the sea, the shallow water, we get a higher temperature. So shallow water, deep water, lower temperature, higher temperature, the same result. So if we are in, you know, a linear behavior, then we will get shallow and deep, same story related to the saturation curve. And they will be both or supersaturated or undersaturation. So what breaks this equality? Okay, when we take into account a more realistic, not only this equals that, we have also evaporation, sensible heat flux, long wave radiation. So we have many things now open and take energy out of the, and we have now thermoregulation. The higher the temperature is, the more all these engines are taking out energy from the system. This is where we break this equality, and this is where we get this behavior. So you cannot elevate the temperature here as you elevate it here compared to what you do in salinity because of energy losses by evaporation and other mechanisms. Okay, I hope I convinced you that now they do not behave the same, and this is why we have in the summer in the deep lake undersaturation and in the shallow lake supersaturation. We can develop that, but I think I'm a bit short in time, so we'll go to the next question. Where do we have salts? So first we understand when, very different between shallow and deep, and then now where. Where in the basin we get the salt layers, and this goes back to the geologists that finally find these salt giants, and they have a certain geometry and the architecture of the basin. And one of the biggest questions they have is why do they see such a thick layers in the deep part, whereas they would maybe expect formation of salt in the more shallow part because of you know, subhas and so on. There the salinity reaches the highest. So geologists have many ideas, but what is actually going on? To do that, we have to take into account the thermal stratification, which means variation, depth and time. Mass and heat transfer, we have to understand how these scalar fields are arranged. And yeah, it is involving hydrodynamics, like we see here, and thermodynamics also, like we see here. Let me go the easy way. Let's take a short video with a robot. We are now going to descend along a cable that was attached. It has a weight on the lake floor. It's a cable with sensors, and it is reaching the water surface with a tension buoy. So it's upright all the time, no slack. Okay, now we are visiting that after about 3 weeks, and we will descend. It was in the end of the summer, so we descend at the upper part. These sensors are this big hobo sensors. You see the cable is black, no salt. We are in the end of the summer. We expect to see here tons of salt crystals, but we see nothing of that. After the full period of the summer, with and here we descend below the thermocline, and we start to observe salt crystals appearing in the lower part and not in the upper part. And this is a very interesting setup, not known from the literature. And it requires some explanation. How do we arrange a basin that is in hydrological stress? Less water is coming than is evaporating. Highest salinities are in the upper part. So we don't have salt crystals there maybe because it's too warm, as I explained earlier. But okay, let's say that this is explained, but why do we have salt crystals in the lower layer? What is supplying salt ions to crystallize in the lower layer of the water body? This is the question. To answer that, I will show you another experiment that the PhD student Ali Arnon, she was experimenting that at home. Same like here, food, kosher, color, and so on. And you see the interface here, it's warm and salty over cold and fresh. Now the interface at the beginning was very, very stable. And now you will see that it becomes unstable. This phenomena of, it is called salt fingering because there are saltier water that are descending down, and also the same symmetrically are rising up. So things start to move here, there is an instability. Why there is an instability? It's not so clear first because this is lighter than this. Oh, density here is lower than this, so it should be okay. But locally, we have a process here that is very interesting. Okay, it's called double diffusion salt fingering. So this is a kind of physical sketch, two-dimensional. We have a perturbation that is growing for some reason. What is the reason? Because that's where double diffusion comes. So we have a fast diffusion of temperature and low diffusion of salinity. And the difference is 2 orders of magnitude. So when you have such a perturbation, heat is quickly transferred conductively. And then you have a warmer part that is getting cooler and start to sink because of the high ion content and the low temperature now. And same the other way. So this is a symmetrical picture. It was found in the 1960s and applied to oceanography in some places, but never as rock forming process, always related to nutrients, very important. And there were also ideas of aqua agriculture to use that as nutrient pump with pipes and so on. But so this is the situation where we have in the vertical, so we have thermohaline stratification, warmer and saltier over less and less, and it is overall stable. This is a situation that happens sometimes in the oceans, and wherever it appears, we will see in a minute that we have this instability. And it always happens when we have the temperature and salinity opposing in their influence on density. So warm makes it lower density, salty makes it higher density, and the overall process, because of diffusion, is these instabilities that tend to grow. Now we have a question. What happens when we are still in oceanography, but we go to the extreme, the saltiest that you can think, when we reach saturation? So when we reach saturation, it's the same game, but we add something. We add a pinch of salt. So now this cooling finger that is going down, it contains high salt ion composition, and it is getting cooler. So it gets super saturated. So it starts crystallizing salt. And the other way around, when this brine, which is a lower salinity, gets warmer, it's getting undersaturated. They all started at saturation. And now this is a very interesting process. On a temperature salinity diagram, it will look like this. If we have the epilimnion and hypolimnion at the summer, so warmer and saltier over less warm and less salty at the same time, the salt fingering will take the daughter of this, will go here to the supersaturation field in terms of thermodynamics. So it will be supersaturated, it will form crystals, and the other way around under saturation. So we simulated that with my colleagues. I have an NSF-PSF program with colleagues from Santa Barbara, and they know how to solve that. You know, the hydrodynamic equations of Navier-Stokes equations, continuity, and then the transport equations of temperature, salinity, and crystals, and equation of state, and the solubility, which is the expression of thermodynamics. When they solve all this, they get these two-dimensional charts of, so these are two-dimensional simulations starting with warmer. And so this is for temperature, salinity, temperature deviation, and salinity deviation from saturation. So let's start with temperature and salinity. We start with warm and salty over cold and less salty. And with time, we have the development of the salt fingers. They develop. You can see how the fronts here are much more fade, and here are much more sharp, the gradients, because of the diffusion, right? This is fast diffuser, slow diffuser. And okay, let's skip that. Let's go to saturation. We start at saturation, but then with time, these fingers are spreading in their behavior. The lower part become more and more super saturated in respect to highlight, and it forms crystals, and the other one is getting undersaturated. So this is a very interesting dipole behavior of the hypersaline water body. So let's see. So first, this can explain our observations with the ROV, right? So we have upper layer, which is without salt, lower layer with salt. The supplier is this instability. That's what we think, and we have many other observational I think, observations that support that. Yeah, so now let me take you still in the oceanography here. So we have temperature and salinity, depth profiles, winter, summer. Winter, we have fully mixed because we have cooling and evaporation. So it's this one, very, very mixed. And in the summer, it's the other one, but for different reason, we have warmer by 10 degrees, 25 meters upper layer, which is warmer, and saltier. Salt is the process here, and here the salinity anyway. And let's see how it looks in terms of the minerals that are forming them. So we still have this cable, but this time we're repeating the cable for 2.5 years. Every month we go to the sea, we take it out, and then put it back. On the way up, we measure the salt crystal thickness around the cable. So here it's 0, it's the summer in the shallow, and in the deep we have some numbers. And in the winter, everything is much larger numbers. So this is after 1 month in the summer and winter, a lot of observations with depth and time. And this is how it looks like in terms of, okay, again, depth and time. Crystallization rate 0, meaning we don't form crystals, even we dissolve. And here, as we go darker, crystallization rate is higher. It's in millimeters per day, which is quite fast. This is why we have problems in the motors in the winter and not in the summer, right? So in the shallow, you move from summer, very surprisingly, the solution, winter, crystallization, and in the deep, we have crystallization here everywhere because everything is fully mixed, so the properties are even everywhere, are uniform. In the summer, we have this two-layer system. So, and I've shown you the double diffusion thing that we have here now explanation for the source of crystallization in the lower part of the water body. Now, as geologists, we are very interested in the active environment. So let's take a look again. Cameras, let's take them down because from the above, everything looks blue. It can be the Lake Tahoe or Dead Sea. We don't have any idea. But when we take the cameras, we can find some interesting things. So here we are in the shallow during summer. So summer, saltiest, but no salt. So you see, this is really like Lake Tahoe. You have boulders we are 10 meters below sea level. Depth, temperature, saltier, and saltier, but so much warmer, so we have the dissolution of salt. So these are pebbles of, chert, gear, so whatever we know from here, chert, limestones, dolostone. At the same time, we go a bit further to the deep. We go deep enough below the thermocline. So we are now in 40 meters or 50 meters depth, deep. It's cooler, but what you see here is salt crystals that are forming. You see this is about 1 centimeter. cubic crystals as perfect as they can be. And they are forming at the same time that in the other part they are dissolving. So here we have dissolution in the shallow. At the same time in the deep we have precipitation of coarse crystals. The coarse crystals are formed over the seascape, and they are growing from bottom upward because of contact of supersaturated brine with lake floor. Now in the winter, at the same time, the same region here, have you been in a snowy region? It looks much smoother, right? Like this. This is kind of snowy salt covering the landscapes, all these pebbles, same depth, 10 meters, but in the winter, highest production of salt, fine particles falling from the top to the bottom. Winter in the deep, instead of the coarse crystals, we have very fine crystals, snowy landscape in the deep. So, and crystal size, the texture, it's very important also for interpretation of, finally as geologists, we typically drill, not me personally, but my friends do that. They have drills this size from many places in the world, and they open the core and they ask themselves, what can I learn from the texture? So here, I will show you that a little bit. Crystal size, coarse, fine, and this is halide saturation. As I told you, we know how to measure a saturation of the brine. So in supersaturated, highly supersaturated, we have fine crystals, whereas in low supersaturation, we have coarse crystals. And the reason is kind of kinetic. The formation of a new crystal requires more energy, more, chemical potential energy to form a new crystal. So this is happening in high supersaturation in the winter due to overcooling. In the summer, we are close to saturation in the lower layer. That's why we have overgrowing of crystals and not formation of new crystals so much. So this is how it looks like in the summer. The coarse crystals are forming under the thermocline. In the winter, I was promising not to use so much terminology, but thermocline is the region where the temperature changes dramatically on the spatial. In the winter, we have these fine grains that are forming everywhere in the water column, a lot of nucleation and the formation of these deposits that we call cumulates. Okay, so now we have a kind of an atlas of salt deposits. We know that in the summer, in the shallow, we get dissolution mostly. In the same time, in the deep part, we have crystallization of coarse crystals. And in the winter, we have fine crystallization everywhere. So now we can go and try to explain salt deposits. And before we do that, so these are modern deposits that this is 1 year of deposition, as I told you, 10 centimeters roughly. It's a bit less, and I'll tell you why. But we have here summer and winter and so on. These are the modern highlights. I will get that there soon. Just to close this question, where? So we see that in the winter everywhere, because of convection, of cooling and evaporation, we have cooler and saltier at the upper, and then everything mixes, formation of salt crystals everywhere. And then in the summer, we have dissolution in the shallow, double diffusion, formation of a deep layer. That in that way, we can move in time, still winter and summer. In that way, finally, we focus on most of the salt materials to the deep part. And this is a very important observation to explain other ancient deposits. For example, from the Messinian, they were asking why we have such an architecture of thick here and shallow here. There were a few suggestions. Now the leading explanation, I think, is ours. We applied that to the offshore salt of Israel. So as I told you, offshore Israel, we have 2 kilometer thick salt. We see that they are getting dissolved here. We think that these are the thermal dissolutions. I will not get into the details so much of that, but This is the basic model that we suggest that finally explains the architecture based, but on all these aspects of hydrodynamics. So these are my kids. Let's go now to the model. That is birthday. Okay, so this cliff was formed about 3 years ago, and in Hanukkah they do not allow us to go anywhere, only to the Dead Sea. So each time we find something else, but my students found this cliff that was forming after one winter storm, and they then exposed very interesting and valuable rock record of the modern. So 1980 is here. Daniel was born in 2003, so you can see, I will show you the unconformity here. There was a very snowy year and a very rainy year, so a lot of rain, and there was dissolution here. And you know, each one is pointing to his birth date. In En-Gedi. Tourism afterwards. So this is the section. We have now a paper on that. Okay, this is the height of the section from the bottom to top. We can identify year by year according to these transitions. The couplets are yearly layers, and we can build an age model. So we have depth and age. And we can identify very, very interesting features here. For example, 1992 was the Pinatubo year, 91, 92. A lot of rain in the region. The dams, including Lake Kinneret, could not hold this amount of water, and they discharged water to the Dead Sea. Instead of going down 1 meter, it stepped up. The lake level rose by 2 meters. And brought a lot of sediments. So no halite precipitation at that stage, because we are in this situation of meromictic conditions with fresher water at the top, no crystallization, and a lot of mud arrived. And this is the muddy layer here. And this brings us here and so on. So we can build the age model, and then we identify also that each part of the section, we have upward shallowing. So this was a deep layer at 30 meters, and then transition layer, and then shallow water, and then we can see in the rock record how things are getting shallow. And yeah, so this is Ido. So this is the 1990. This is the Pinatubo 1991. We see here a lot of mud, but no dissolution. And this is because the marine situation, or we were deep enough at that year compared to the dilution layer. The layer that was influenced by the floods was only 15 meters or so. And the section at this place was below that, so it did not, it was not in contact with diluted water. So this is why we don't have dissolutions at this location, but we do have a lot of mud that arrived here. Now, if we step up, you see here there is another surface when my big boy was born. See here, this is an unconformity. How do you see that? You see that there are layers approaching this in conformed strata, one over the other. So this unconformity was in the same situation, very rainy year, not as much as this one. Still, the level rose by 70 centimeters, and there was dilution. But at this level, at this stage, the level dropped down. So we are now at the same place like here, but now in shallower environment, we feel the dilution, and the expression of this dilution is a cut of all these salt layers that were above, and they were dissolved.
How many years of salt was dissolved in 2003?
Not so much actually. We can even less. So only about a few years, like this amount about. Because how do we know that? We follow this. During the winter, I'll tell you where to look at that. You can follow this interface for kilometers. So you can see exactly what it is cutting and not. So it's about this amount. This is this interface of 2003, beautiful. Yeah, this is the uniformity. You see the earlier layers that are cut by this truncation surface, and from there on, it took about one more year. Yeah, so but it takes 1 year about to take out all the extra fresh water and then drought again. And so this is kind of climate, right? Hydroclimate in the rock record. So the modern rock record archive, what did we learn? We have annual valves. We can identify coarse grain, fine grains, depending on depth. Grain size and texture are meaningful for saturation environment. We describe here how the sections get shallower, and the solutions are very important to them because of dilution, part of them because of thermal, because of overheating. So we have this solution of salt rocks. Let's move forward. What about?
We are already at noon.
Already at noon. The consequences. I had some question of how fast, where, when, and so on. I think we answered them. So I will go to some optimism. So the level is dropping. What do we do? Is it a catastrophe and so on? So generally, when we see lake level drop, our feeling is not good. But there are beautiful things around. And regardless what we do today, from now on, 20 years from now, the level will drop. Okay, this is a good assumption. And now the question is if we continue as the state of Israel to make signs of no entry, too dangerous because of sinkholes and so on, very good reasons, but too much of safety, I think. So the balance, it is unbalanced because as you see, many things to do there. And for tourism, again, you can have my contact. I can strongly recommend you to take your friends like I do. And we published a report that is suggesting to turn the concept to another direction, more positive. The situation is now, is it a catastrophe? I find that no, it's very beautiful. Should we leave it like that or other way? This is another discussion. But right now we have to develop this region, allow people to work, enjoy safety. We in the Geological Survey, not my group, but other groups, know where the regions are sinking and not, or more dangers are. So we can help a lot to manage these things. This is my optimistic part. And thank you for listening and yeah.
Maybe 1 or 2 questions. Okay.
So I was wondering if I looked at the dots picture and you noticed that you have more salts in afterwards. So each year would be say something like that.
Yeah.
And where does the sediments that you why do you not get there? What is the sediment?
Which sediment? So, let's start with the first, maybe. No. Yeah, here.
So I noticed that you have more thicker salt layers.
So
above 2003. Okay, so we go to 2000.
Yeah.
Or something like that.
So when we go to the age model, let's assume that we are okay with the age model. It's questionable, but let's say that it's okay. So now we can have the thickness with time, and what you can see here, how the thickness when you normalize it to the lake level drop. So we have here 9 centimeters of salt layer per 1 meter level drop. Here it's only 5.6, and here it's only 3.6. Why the rate is declining per 1 meter level drop? Because of the dissolution and so on. So the dissolution here is not 100% in this location, in other locations it is, but we do see how shallowing is related to less and less salt deposits, and this is goes back to the no, other direction. Okay, to this model. So you see, this model, as you go down, as you shallow, you get so as you shallow, you get less and less precipitate salt, right? In the deeper part, you have more salt. In the shallow, you get less. So it goes well with our reconstruction. So, Niti?
Yeah.
They had higher evaporation. Less rainy and warmer years.
Yeah.
2005, 6, 7, 8, 9.
So here,
so the layers look thicker altogether.
The
The rate is slower. The rate is per meter maybe less.
Yeah.
But you have more evaporation probably. The declining of the water.
so this is already normalizing the declining level. So this is already taking into account the net water loss. So it's thickness of precipitates per 1 meter of water loss. If there is 1 year with more water loss, it is already taken into account.
Just one more question. I know you did work about the environment.
Yeah.
How does that?
It's a good question. My observations were until 50 meters, and the end brine is, so it's between us, right? I can share everyone, but it will be a bit heavy. But yes, so it's below that. Yeah.
Very general question. I mean, you're talking about sodium chloride, alate.
Yeah.
But there are a lot of different salts.
Yeah, it's a good one.
So is there any interference? Because
Yeah.
salinity is different, then precipitation different, and always movement or instability might be affected by other salts.
Yeah. So first, thank you for the question. I should have kind of declared that in my, at the beginning of the declaration. Yeah, I oversimplify that by looking at water and the sodium chloride. In fact, there are more dissolved ions. They are used in the southern basin for formation of potassium-bearing salts, right? In the southern basin, they take the same brine, they evaporate it more, they take out the sodium chloride by precipitation. They don't need this mineral there. But then at the end of the process, they continue from one pond to the other. At the last pond, they start precipitating potassium-bearing minerals. And they produce it to the markets, worldwide fertilizer. So it exists there. It's very important. In our case, where do we find it? We find it, we do see it. So I think that our oversimplification is okay. No, I don't have it here. But let me say it this way. To your question. So if we were only water and sodium chloride, only depending on temperature, but let's fix the temperature. There is a certain salinity of saturation, right? You can add more and more salt at some level, but that's the maximum salinity you can get. If you add at the same time other ions, the saturation will be different compared to the total salinity and so on. So this is how we see it.